what's going on with that area. Thanks for joining us, and please go ahead.
Okay, thanks. Thanks for the invitation, Alexei. It's very nice to be here. So what I'm going to try to do is to do a review of the kind of things that we've been doing using twisted Teguchi-Kawai reduction. And this is work that I have done with a lot of people, with these people. And more recently, I've been working with Claudio Bonanno, who is a very good postdoc that we have in Madrid now, and Kenichi Ishikawa, and Tony González Arroyo, and Masanori Okawa, but there were more people involved in previous stages of this work. So I thought that it would be good, let me see if this works, yes, to start not directly presenting the results of twisted Teguchi-Kawai, but doing a bit of a review of what's the status of this and how is, when it is working and when not, and the sort of problems that can arise. So I will do a brief historical account of Teguchi-Kawai reduction and twisted Teguchi-Kawai reduction, and then I will present in the second half of the talk the results that we have. But before that, let me start by saying that there is a very large amount of work that has been done on the lattice for large N gauge theories using what I call the standard approach to large N gauge theories. And for instance, you have here the meson spectrum and the decay constants. This is a rather old paper, but I think probably for the meson spectrum is the more complete to present using this kind of approach. And typically in the standard approach, what one does is to simulate at various values of n. The values of n that can be reached are not that large, typically of order 10, and then extrapolate to the large n limit. So for instance, here you have results at various values of n, and the purple band is the extrapolation to n infinity using, you can see here values ranging from 2 to 7, which is typically the usual. They have here SU 17, which is somewhat unusual to get there. And there are a very large number of works, many of them by some people that is in your collaboration. So you know probably all these things very well, concerning glue balls or mesons, the string spectrum, theta dependence, topological susceptibility, many things. And for this, I recommend two reviews. One of them is a bit old by Marco Panero and Biagio Lucchini. And then there is a recent one that has been presented in one of the plenaries of the lattice conferences by Pilar Hernandez and Romero Lopez. That's a nice review of the kind of things that are being computed on the lattice for large N gauge theories. Okay, so in this talk, I'm going to take the alternative approach that is using volume reduction. And I'm going to try to convince you that this is a very efficient tool for large N lattice studies, in particular because it allows to go to very large values of n, of the order of 1,000. And for instance, in this paper, Tony and Masanori have computed the string tension going up to values of n this large, right? So it's an approach that is complementary to the one that the standard approach is doing. Also because the twisted Teguchi-Kawai allows you to get the result in the infinite, basically in the infinite n limit. But the kind of corrections, 1/n corrections that it provides are different from the standard ones. They are more related to finite volume effects. And then if one wants to study 1/n corrections for SUN gauge theories, one has to use the two setups in a complementary way. Okay, so TEK would give for you the large N limit that you can use to fix the extrapolations to large N using standard approaches. So the two techniques have to be combined if one wants to extract, for instance, 1/n corrections to the theory. And let me also mention that this approach of volume reduction is a particular instance of what is called in the continuum volume independence. And the use of twisted boundary conditions, has become also very fashionable in the context of generalized global symmetries and these kind of things, a particular instance of that. So theoretically, all these ideas are very appealing and lead to many, many different things that are very interesting. By the way, I don't see raised hands or anything, so feel free to interrupt any moment and ask questions, but do it, disconnect your mic and do it aloud, because otherwise I won't see the chat or the raised hands, okay? Interrupt me any moment. Okay, so a very basic introduction to Teguchi-Kawai reduction before going into TEK. The idea is, very nice, but simple, is the fact that an infinite volume lattice is equivalent to a matrix model that lives on a single site lattice, in principle with periodic boundary conditions. And what one does is just to replace the independence of the link by a matrix, 4 matrices in the case of 4 dimensions that are not don't have any space dependence. So the equivalence between these two models on the lattice holds on the basis of loop equations, Swinger-Dyson equations for the Wilson loops. And in principle, it is exact, but there is a condition. I mean, this relation holds provided that the trace or the expectation value of the trace of any open Wilson line in the reduced lattice averages to 0. So what is an open Wilson line? These are open Wilson lines, sorry, in the original lattice, for instance, something like this, okay? These lines in the original lattice due to gauge invariance average to 0, have the expectation value that is 0, but in the reduced lattices this is not the case because due to the periodic boundary conditions, any of these lines is closed on the reduced lattice. They are computed in terms of these matrices in this way, and in principle they don't have necessarily to average to 0. So there is a requisite that gives to you that these expectation values are 0, and it's invariance under the center symmetry. Okay, if any matrix can be multiplied by a center element, and if the center symmetry is preserved, these lines will average to 0, and the equivalence will hold. The problem with the original proposal by Eguchi and Kawai is that this symmetry is spontaneously broken. And this is something that was seen at the very beginning by Banot, Heller, and Neuberger in this paper. And indeed, in the original paper by Eguchi and Kawai, there is a footnote at the end of the paper saying that beware that these people have pointed out that the symmetry may be spontaneously broken at weak coupling. So let me explain why it is spontaneously broken at weak coupling. The idea is very simple. With periodic boundary conditions, the zero action solution is of this form. It's a diagonal matrix with constant angles. And if one integrates out the quantum fluctuations and looks for the effective potential, the result looks like this. And it is such that for dimensions larger than 2, the angles tend to align, and then they break the symmetry. Okay, they become all equal, and then you get something proportional to the identity, which has a non-zero trace, and they break the symmetry. So the fixes that people did at the time of Eguchi-Kawai were 2, TEK, which is change the boundary conditions from periodic to twisted boundary conditions, and as introduced by Toft, or quench the Eguchi-Kawai, QEK, which was basically freeze the angles. In that case, you simulate basically the matrices that make the U-Mus diagonal, and then average a posteriori over the angles with a distribution that is uniform, okay? So the situation was like this in the 80s. There were a few simulations done, and things seemed to work, but okay, computers were not sufficiently powerful. So in the 2000s, more extensive numerical simulations were performed, and it was seen that in weak coupling, there was a spontaneous symmetry breaking. Things didn't work.
Question.
Yeah.
So is there a phase transition where the distribution of theta switches from uniform to bunched up or something?
So in a strong coupling on the lattice,
it's uniform, right?
Yeah.
Yeah.
So there is a phase transition at large n that separates the strong coupling phase from the weak coupling phase, and then in the weak coupling phase, things go wrong. Yeah.
Mm-hmm.
So there is a phase transition. Yeah. At the strong coupling, it works, but the strong coupling is not the continuum, so we don't want.
What order is this transition? Is it like the gross width?
I think so, but I don't remember exactly. But I think so. Yeah, it's a gross width.
Like in the one plaquette model, you see.
Yes, it's a one plaquette model. It's exactly a one plaquette model. So it's gross width and phase transition. Okay. Yeah, it's a one plaquette model because you only have these 4 matrices living on a plaquette. Yeah.
Okay. Thank you.
Okay. So both of them failed. There were several works showing that there was a failure of the 2 proposals, and there have been fixes to the 2 proposals also. In 2010, González Arroyo and Okawa proposed a new set of boundary conditions for TEK. And more recently, in 2020, Herbert Neuberger has also proposed a fix for QEK, but I don't think it has been taken up in numerical simulations. There have been extensive numerical simulations in which I have also been involved for TEK. So let me mention that there are also other alternatives, which I will not discuss at all in this talk, like continuum reduction or the addition of massless adjoint fermions or trace deformations by Kotbun Unsal-Jaffe and Unsal-Al-Jaffe. But I will not enter in these topics during this talk. I will focus on TEK. So to understand a little bit how to cure the problem in TEK, I will start by introducing twisted boundary conditions. I guess all of you know about this. I will try to go fast, but it will be useful for me in order to explain how to address the problems of TEK. So twisted boundary conditions have been introduced by Toft in the late 80s. And basically, the idea is that if you want to have periodicity of local observables on a torus, I mean, you have the gauge theory living on a torus, you only have to require periodicity of the gauge fields up to gauge transformation. So for instance, if this is my torus and I move the gauge field along this line, when I come back, I have the freedom to insert gauge transformation. These are called the twist matrices or the transition matrices. So the gauge field has to be periodic only up to these matrices. There is a consistency condition that has to be satisfied. For instance, you have the torus here, it's two-dimensional torus, and you move the gauge field along this direction or along this direction, you have to obtain the same result. But since the gauge field is in the adjoint representation, it is blind to the center, so these two matrices only have to be equal up to an element of the center of the gauge group. So there is this consistency condition reflects the fact that the gauge fields are living in SUN mod Zn, and then this is the consistency condition between going this way or going this way up to an element of the center of the gauge group that is parameterized in this way, and this tensor is an antisymmetric tensor of integers. This is what is called the twist. These are twisted boundary conditions. This twist cannot be removed by a gauge transformation. It's a set of integers that characterize the bundle and define the theory on the small torus, okay? So for TEK, there is a particular choice of twist that is done. Let me assume that I'm living on a torus of d dimensions times r to the n. And then the twist that is taken for Eguchi-Kawai reduction takes this form. So it's an element of the center of the group. This epsilon mu nu takes this form. And then you have k over n hat, where n hat depends on the size of the dimensions of the torus you are considering. For instance, if you are taking a T2, it's directly n. But if you are living on a T4, then it's the square root of n. And for this type of twists, it is possible to choose the twist matrices to be constant and satisfy this relation. And moreover, whenever these two numbers, k and n hat, are coprime, this set of twists are what are called irreducible twists that are characterized by the fact that the only matrices that commute with all the gamma mu's are proportional to the identity matrix. So in that case, multiplying the gamma mu's, one can generate by multiplication a basis of the Lie algebra of UN in this way. And n squared minus one of these matrices are traceless. So one can use these matrices as a basis for the Lie algebra of the group. And this is very useful because then one can implement a Fourier transform that implements directly for the gauge fields that implements directly the boundary conditions, these ones. And this is how it looks, the Fourier transform. So you have a sum over momenta exponential of e pi epx, and then these are numbers. And all the color dependence goes in these matrices that are momentum dependent, a momentum dependent basis of the Lie algebra, okay? So remember that, the only condition for this to be satisfied is this condition here, and it is very easy to construct solutions using this matrix multiplication with integers here appropriately chosen. And what is more important, the only thing I want to stress is that the momenta that appears here is quantized in a very particular way, because it's not quantized in units of the periods of the torus, of the original torus, but it is quantized in units of an extended period that contains the color degrees of freedom. So there is an effective size that is defined in this way. And the other particularity of this momentum expansion is that since the Lie algebra matrices are momentum dependent, the structure constants also get a momentum dependent. I will go over this in the next slide in more detail. So using this Fourier transformation, it is, the two things that one can derive from this transformation is the fact that there is an increased effective volume, at least in perturbation theory, parameterized in this way. So all the momenta that are quantized along the compact cycles that have twisted boundary conditions go with this effective volume that is defined in this way. And I recall that for the case of T4, which is what we will use for TEK, n hat is square root of n. And then the other important thing is that there is, when you derive the Feynman rules, a non-commutativity in the vertices of the theories, because the structure constants, for instance, for the 3 gluon vertex, get this momentum dependence. So these are precisely the Feynman rules that define a non-commutative gauge theory. So there is something called Morita duality that tells that these theories with twisted boundary conditions and rational values, this is what is called the non-commutativity parameter of the non-commutative gauge theory, with rational values of the non-commutativity are equivalent, non-commutative theories with these rational values of the non-commutativity are equivalent to gauge theories with twisted boundary conditions, right? But this was something that was formulated much before non-commutative gauge theories started to enter the game. So now that I have all this set up, let me go back to TEK and answer the question whether the symmetry is respected in perturbation theory for the TEK lattice. So I will do the analysis that was done in the original times by González Arroyo and Okawa to substitute the Eguchi-Kawai reduction by TEK. And the argument is very simple. I mean, if we are in this plaquette model, in this one-point lattice, for Eguchi-Kawai, the action on the lattice looks like this. This is the plaquette constructed out of the 4 matrices with periodic boundary conditions. So now we are going to implement twisted boundary conditions on this lattice. And there is a change of variables that allows to do it in a very simple way. So the only thing one has to do is multiply the plaquette by the twist factors in this way. And then it's very simple to see what happens in perturbation theory. If you look at the solutions, the zero-action solutions for this model, given that the twist matrices, satisfy this condition, it is trivial to see that taking the U mu is equal to one of these matrices gives you a zero-action configuration, okay? But then I have told you that if one selects the top flux reasonably, being co-prime with this n hat that I have defined, these matrices are all traceless as far as these SNs are smaller than n hat. So this means that I construct open loops of this way. These are just open loops that wind S naught times in the direction 0, Sn times in the direction n. All these open loops will be traceless. And therefore, the solution of zero action preserves the symmetry, except for loops that are of length n hat. So there is a symmetry, a set n hat symmetry that is preserved at zeroth order in perturbation theory, contrary to what happened in the Eguchi-Kawai lattice, okay? So when n goes to infinity, this is sufficient to restore the symmetry at large n, and in principle, this was the solution proposed originally for twisted Eguchi-Kawai. Remember that for T4, n hat was a square root of n, so there is a set square root of n to the d symmetry that is preserved by the zero action configurations. So when does this fail? The choice of the Toft flux, this K, is critical. So the original proposal of Okawa and Tony was to set K equals to 1 and then take the limit to infinity. And this is precisely the case that doesn't work. Indeed, if you fix K and send n to infinity, fix K to any value and send n to infinity in such a way that K over n goes to 0, the symmetry is going to be spontaneously broken, and then things are going to fail, okay? So what do we have to do to select the top flux to avoid the problems? I'm going to go in a little bit of detail through this story. Okay? So the first thing that was seen by Mike Tepper and Vairiños already in 2007 is that there are some symmetry breaking solutions, for instance, taking all links to identity is a configuration that breaks the symmetry. They have higher action than the twist matrices, but they may be entropically favored. And in weak coupling, sometimes they are, okay? So the solution that Tony and Masanori found for this problem was to scale the top flux with n. So you have to scale k with n in such a way that the ratio k over n hat stays constant when you take the limit, okay? Now, I mean, we have analyzed these conditions a little bit more in detail, and we can go, I mean, we can be a little bit more precise. So let me explain a little bit how this goes. It is a little bit, well, maybe complicated, but I'll try to explain what are the conditions that one has to set for the top flux to avoid problems with TEK. So I'm going to go back to the continuum and take back the connection that there is between twisted boundary conditions and no-commutative gauge theories. And it is well known since long that there are what are called tachyonic instabilities in perturbation theory in the case of non-commutative geometries. And indeed, already long ago, Guralnik, Lasteiner, and Lopez have studied these tachyonic instabilities also in relation with twisted boundary conditions. So I'm going to present here some results that we have done analyzing the case of T2 times R with Jan Mills in T2 times R, analyzing in perturbation theory and also using numerical simulations, in which cases these instabilities in perturbation theory arise. And I'm going to try to explain why it's important for the working of TEK. Okay, so if you work in a finite volume, Toft showed us that I mean the physical states are parameterized by a quantum number that is called the electric flux. And with twisted boundary conditions, it is easy to see at leading order what is the energy of these electric fluxes because it's just given directly by the momenta. And the momenta, I told you, is quantized in units of n hat times L, this effective volume, okay? So in principle, the twist forbids zero momenta, so all these states in the small box will be gapped. We can try to do a little bit better and go further in perturbation theory by including a one-loop correction, the self-energy corrections to this leading order term. And there is where the problem appears, because the self-energy correction is negative, and moreover, it can become infinite. So I'm plotting here, for instance, for the case of n equals 149 and k equals 1, the result of plotting E squared, this is the electric flux energy squared at one loop order, versus the volume for different electric fluxes. And you see what is the problem. This energy squared becomes negative. This is why it's called the tachyonic instability. Okay, the self-energy drives the E squared negative for several of the fluxes. And this is generic when one tries to keep k fixed and send them to infinity. So, of course, this will not become negative in a numerical simulation. This is, for example, the result of a numerical simulation where we have fixed n equal to 17, k is equal to 1. And moreover, when you make the volume large, the electric fluxes will, because we are in a confined setup, I mean, in a confined theory, will grow linearly with the size of the box, and then these energies will go up. But what you observe here is that, I mean, one starts with the perturbative formula. This is a tachyonic instability, and in this regime, the electric fluxes become very light, and in principle, the assumption is that they condense. So this is a problem for adiabatic continuity, because you start in the small box, you try to go to the large box, and you may find a phase transition in between that spoils adiabaticity, okay? So there are ways to avoid this by scaling the flux. This is, for example, a case where we have done n equals 17 with k equals to 3, and you have here different electric fluxes. They all stay above 0. So in this plot, all the points represent numerical data obtained in a Monte Carlo simulations, and the lines is a fit that we have done to the data with a very simple assumption that is the following. We combine in quadrature the one-loop formula with the Nambu-Goto string formula, okay? And as you can see, the lines describe very well the results of the simulation. So this is an empirical formula, but it's a very good qualitative, even quantitative description of the data. We have done simulations for many cases, okay? So the condition that one can impose in order to avoid... Yeah.
Sorry, so I have some confusion about the k=1 case.
Yeah.
If I imagine fixing the twist k and taking n to infinity, looking back at the original formulas for how the twist enters things, it seems to me like the twist will become trivial in that situation as you take n to infinity, no? Because the twist is the 2 pi I k over n, and if k is fixed and you take n to infinity, it becomes 1. So it doesn't do anything. So in retrospect, is that a reason, is that kind of argument a way to predict like k=1 should not work? Is it that simple?
Yeah, because the solutions are still, I mean, if you just look at the perturbation theory, the zero action solutions at lowest order, they are still traceless, right? So
it's sort of, I agree it would seem that way, but at the same time, this other perspective of just asking if you really have much of a twist at large n, you might think that physically it shouldn't matter.
Yeah.
Unless k scales with n, in which case it will matter.
Yeah. So this is true. I mean, in principle, yeah, you could have expected. I mean, you're approaching the case of periodic boundary conditions in a sense.
That's what I'm saying. Yeah. That I should physically approach that case, and so sort of in that respect, maybe one could argue that. Okay.
Yes.
Okay.
But well, as we will discuss in a moment, is quite generic. I mean, the fact that you can find this kind of instabilities. I'll go to that in the next slide. So in principle, this is the condition, okay? Oh, sorry. And this can be rewritten in a condition for, I mean, if you insert the value of the string tension and all these things, this can be rewritten in terms of a condition for the flux and n that looks like this. So it's the minima over integers that are coprime with n, the integer, and this quantity here represents the distance to the closest integer, okay? And this quantity has to be bounded from below. In this particular case, is 1/10, okay? But it has to be bounded from below. And I mean, this condition has been derived in this paper. Fernando Chamizo is a mathematician. And actually, this quantity, this quantity is relevant also in other contexts. I mean, we derived it in the context of T2 times R, but it appears in many instances. For instance, if you go to the 4 torus and you try to study what are the contributions of non-planar diagrams in perturbation theory, for instance, to Wilson loop expectation values, or in this case, it was we were analyzing the matching of running coupling definition that uses twisted boundary conditions to the MS bar coupling. You can see that if you plot the contribution, I mean, these are the contributions. The theta-dependent diagrams are the ones that are non-planar, because in the planar limit, all theta dependence has to disappear. And indeed, it disappears. I have scaled this quantity with the effective volume. So typically, the contributions that are theta dependent to the Wilson loop expectation value are suppressed with effective volume, okay? But there are particular values. For instance, imagine that you try to fix theta to 1/4. 1/4 is okay, but if you approach 1/4 by a set of rationals that go to 1/4, I mean, a fraction, rationals, I don't know, 11/41, 101 over, etc. There's going to be a different contribution. I mean, these diagrams are enhanced and the convergence is slower. It goes at a slower rate. And this rate of convergence is controlled by this quantity set mean that I have told you before, okay? So this is a relevant quantity also in other contexts. So the question is basically, can we satisfy this condition for the 't Hooft flux in such a way that we are safe from these instabilities in all cases? So if I have n, if I fix n, can I choose k? K bar is the modular inverse of k to satisfy the bound. So it turns out that this is a conjecture in number theory that is called the Zarembas conjecture that is unproven. So there is no general solution to this question. But there's been a recent 10 years already, results that say that it is possible for almost all values of n. Right? And actually, there is something very nice, because it turns out that the largest value of set mean, the one that will be larger, is obtained for Fibonacci numbers. So it's an instant in which Fibonacci numbers again appear, which is very nice. So if one takes a sequence going to large n in this way, so you select k bar to be the I-2 number in the Fibonacci sequence and n to be the I number in the Fibonacci sequence, you never encounter the problem, okay? So then this set mean is bounded by this number, 0.38, which is in principle larger than the bounds, and there should not be a problem, okay? So taking the flux and n along the Fibonacci sequence seems to be the best way to avoid problems when you're doing TEK or any kind of these, I don't know, volume independence, adiabatic continuity games in town with twisted boundary conditions, okay? So what is the game for us for doing TEK? I mean, we have this effective volume that in principle contains L and N. And we want to take the large n limit in a particular way. So we are going to keep L fixed, the torus period fixed, and we are going to send n to infinity in such a way that the effective size goes to infinity. In principle, this controls the dynamics. So in that limit, we are reaching the top limit. Planar diagrams die away, and we are in the top limit. For TK, the period is set to the lattice spacing. The effective volume is the lattice spacing times this n hat. And we will work as if we were on an n to the 4, n hat to the 4 standard lattice. For T4, it will be a square root of n to the 4 standard lattice, as far as we have the flux appropriately chosen, okay? So if you choose the flux to satisfy the bounds and use twisted boundary conditions, you will be able to play the TEK game in principle without problems. I mean, this is not a proof, but it's an argument to say that it will work. And we have done extensive numerical simulations up to very large values of n, and we have not seen evidence of spontaneous symmetry breaking in any of those cases, okay? So, well, it took me a bit longer. Yeah, okay. So let me go to the results for TEK. So what we can do with TEK using this setup. I don't know if there are maybe questions up to here or I continue. Is it okay? I continue. So let me show you several results that have been obtained using TEK. So the first one is the string tension at large n. This is not my work, but Tony and Masanori have obtained the string tension from extracted from Kreutz ratios. And these are, for instance, the results. This is the ms bar, the lambda ms bar in units of the string tension as a function of 1 over n squared. And you can see here values obtained in standard lattices simulated with standard ends, okay? And this is the result of obtained with TEK for n equals 149, k equals to 41, k equals to 9, which, as you see, is perfectly compatible with the large n extrapolation of the standard approach, okay? So this is what I was saying, that the advantage of TEK is that with the large n simulation, you are basically on top of the infinite volume result, okay? They have also derived the first correction to this to the string tension, obtaining a result that is different from the expected Nambu-Otto result. But as I say, this is not my book. So something else that we have done, which I think is sort of cute, there is nowadays something very popular in the lattice community that is called the gradient flow, which is used for many things, in particular for deriving running coupling, I mean alpha strong. And the idea is basically that you introduce a fictitious time that is called the flow time, and you evolve the gauge field along the steepest, I mean the gradient, I mean the coefficients of motion, okay? So the effect that this gradient flow has is to smear the gauge field on a ball of radius square root of 8t. And people have defined running couplings using, for instance, the energy density for these flow fields, defined at a scale, at a momentum scale that is characterized by the flow time in this way. And there are also finite volume schemes where this momentum scale is tied to the volume of the box. So if you have twisted boundary conditions, I have argued that the volume of the box is this effective volume that combines color and spatial degrees of freedom. So in principle, one can run the coupling with this effective volume. So now if you go to TEK, the effective volume is the lattice spaces times n. So something that is nice is that here you can run the volume. I mean, you can run the scale of the coupling directly with the rank of the group with n. And this is something that we have done. Well, I'm not going to stop in the details, but in principle, you could determine the running of the strong coupling constant in the large n limit running with n instead of running with the size of the box, which is one of the consequences of this volume independence kind of game, right? So let me go now to the meson spectrum that we have also studied. So we have studied the meson spectrum in the NF over n going to 0 limit. There is an issue with fundamental fermions and twists because fermions in the fundamental representation are in principle not compatible with twisted boundary conditions. But there are several ways to circumvent this problem. For instance, one can introduce extra flavors. And then you can combine translations by a period on the lattice with rotations in flavor space to compensate for the twist. One can also replicate the lattice and to remove the twist and then define the fermions in the extended lattice. No? So this is what Tony and Masanori have done. So for instance, if you start with the link in the plaquette, I mean the one plaquette lattice, and you apply the boundary conditions, you can construct any Wilson loop, okay, doing this. So the trick is basically to replace the independence of the links by this kind of game, where you insert these matrices that I have told you before can be constructed out of the gamma mu's. And then you can work out how the Dirac operator for Wilson fermions, for instance, looks when you do this replacement. Okay, you can work it out a little bit, and it can be diagonalized using a Fourier transform in momentum space. And this is the final result that comes out. So you have a Dirac operator analogous to the Wilson Dirac operator on the lattice. But now, I mean, this is, for instance, the Wilson term. But now you have some matrices that depend on momentum in this way. Some faces, the links, and then these are the twist matrices that are representing here translations, basically. So using this Dirac operator, one can construct correlators of meson correlators on the lattice and extract masses in that case. So we have done this for several states, for instance, the pion, the rho, and these states, A0, A1, B1, that have these spin representations, obtaining well, results that I'm not going to discuss. This has been done with lattices with n equals 299 and 361, several values of A. So these are values in the continuum limit, in the chiral limit, assuming that the pion mass goes to 0, in the limit in which the pion mass goes to 0. And we are at present going to larger values of n. For instance, oops, sorry. I can show you the pion decay constant as a function of the pion mass extrapolated to the chiral limit. And this is the result, for instance, for n equals 3 with 2 flavors that is in the flag world average value. The difference is not very large, but these are the kind of things that we can do. And in this plot, I have included results that go with n up to 529, 841. Okay, so meson spectrum we can do. Global spectrum we cannot do for the moment because TEK doesn't have time dependence. I mean, the global is a two-trace operator, and correlators of double traces are not easy. I mean, we cannot easily do. So for the moment, there are no globals in this game. Okay. Something else.
How do the numerical results compare with real-world data? So, like how sensible is real-world to n? Maybe that's kind of question.
For instance, in FPy, you can see here what's the difference, right? This is real world. Mm-hmm. For the masses, the difference are also not very large. I don't have a plot, but the difference are not very large. So there is the question of whether, I mean, this, for instance, they not, this is a very difficult state also for us. There is a debate of whether it is degenerate or not with the raw. Here it comes very close, but okay. I'm not sure even there is a experimental well-defined value for this quantity here. But the numbers are not very different. I mean, are not very far away from the real world. Yeah.
Can I follow up on that? So for example, picking up on FPI, comparing it to the real world is very nice, but of course the real world is not large N. There's, I mean, but people, I think, have done calculations of FPI and other meson masses using standard lattice increasing N.
Yes. So this compares quite well with those results.
So it's within statistical error, it's the same, or okay.
So the only thing is that, I mean, most of those results are not extrapolated to the continuum limit. Okay, they are done at a fixed value of the lattice spacing.
I see.
So there are, I mean, this is extrapolated to the continuum limit in the chiral limit. So, for instance, I presented at the beginning results by Gunnar Bali for the meson spectrum. This corresponds to one value of the lattice spacing. And for some states, for instance, they note for the raw also, they observe quite significant lattice artifacts, I mean, dependence on the lattice spacing. So there is a thesis by by Castagnini where they try to do, for some of these states, a continuum extrapolation. And for instance, for the raw, although the result in the paper by Bali et al. Does not agree very well with this one, if you look at the continuous extrapolation done in the thesis by Castagnini, the continuum extrapolations agrees well with this result. So in principle, this match well the results that people have with the standard method whenever they are available, because as I say, continuum extrapolated data for these quantities are not, not yet available.
Margarita, can I ask a question regarding the Bali? I mean, work. What was the action they used? The fermionic action, that was Wilson or Wilson?
Wilson. I think it was Wilson without any improvement.
Okay, fine.
I'm not completely sure, but I think it was Wilson.
Okay, thanks. I'll look at the publication. Thanks.
Yeah. So I mean, the best results, if you look for the thesis of, I think it's on the, it's probably on the web, the thesis by Castagnini. And there are also some proceedings where they try to do a continuum extrapolation also of some of these states. These are the best results are there. Yeah. Okay. So concerning the chiral condensate, we have computed it in different ways. I'm not going to stop very much there. But I can show you, for instance, here, the condensate scales like n, and this is the values we obtain in the continuum limit as a function of the pion mass, extrapolated to 0 pion mass. This is the result that we had in this paper, which had much larger error, but now we are including larger values of n, and we are able to pin down. This is preliminary yet, but we are able to pin down the error, and well, this is the real value world. Okay. Again, concerning the value of this, there are some results by Hernandez and Romero Lopez at one value of the lattice spacing, and there are some results that appear more or less at the same time as ours by Tom de Grand, also trying to do a continuum extrapolation, and in principle this number is compatible with the continuum extrapolation, but I mean there are large errors involved in all the cases. Okay, so okay.
Question.
So yeah.
Yeah, I assume someone tried to calibrate this method, say, against something where we know the solution, like say Toft model, or has anyone tried?
Two-dimensional QCD.
Yeah.
Yeah, we did some two-dimensional QCD at the beginning of the thing.
Does it agree?
Does
I mean,
it agree?
There we know exactly the large N mass spectrum, right, of meson.
Yes, we didn't really finish that result, but in principle, yeah, one should
I think it's it's much simpler and would be a good test. No,
yes. I mean, we started that project but never finished completely. And
So
as
it's
far as
not
I remember,
something
it
that's
was
in the
maybe 10
literature.
years ago or so, or maybe a bit less. We found good agreement, but okay, I would have to go back to that because I don't remember anymore the details. But
Even excited mesons, like because for
no,
12
excited
told us
mesons
everything.
excited mesons we didn't compute. But yeah, it would be it's in principle, yeah, a very good testing ground, of course. But okay, in principle, this you can compare. I mean, there are many ways to simulate, as I said, Lagen, not only TEK, and in principle, one can compare with that. The only thing is, as for the string tension, for instance, in the string tension case, this comparison has been done. I mean, simulating at several values of n and then extrapolating and getting the same result with TEK. In all these other quantities, there are not continuum extrapolated precise results at Lagen for many of these things. So it's still, yeah, in principle. The results that there are, they agree well. So I would say it's okay, but yeah, I agree that yeah, QCD2 is a case where you can just beat it. In principle, yeah. Let me say that in 2 dimensions, even the standard Eguchi-Kawai would work because 2 dimensions doesn't have a problem, even for the standard Eguchi-Kawai.
I see.
It's 4 dimensions that has a problem, D larger than 2. Okay.
Margarita, one last question. I'm sorry. What kind of statistics are we talking about? I mean, the statistics you just showed.
For this?
Yes.
So we typically have, for these cases that are the ones 289 and 361, we typically have 800 configurations or so.
Okay. Wow. Okay. Good. Thanks.
So let me now go to something else that we have also analyzed recently, which is n equals 1 supersymmetric Yang-Mills on the lattice. The fermions, when they are in the adjoint, they can be also automatically reduced, okay? Because the adjoint fermions work like the gauge fields. I mean, they are blind to the center, so you can also put them on the reduced lattice automatically. And they can be simulated. So we have attempted to compute the gluino condensate. Let me say that the results for the gluino condensate are available using instanton-based methods. I mean, there are predictions of what is the gluino condensate. And the gluino condensate in units of this lambda in the NSVZ scheme, there are 2 different results or 2 different predictions for this number. One of them is called the strong coupling result, which is basically based on computing, saturating the endpoint function of lambda lambda with 1 instanton, and then using factorization to compute lambda lambda itself. And in the Lagen limit, it gives a result that basically scales like 1 over n. And then there is the weak coupling approach that is supposed to be the good one, which gives 1 for this number. So in the Lagen limit, they differ even in the behavior, in the dependence on n. The weak coupling result has been obtained in different ways, for instance, using monopole constituents of instantons, or even more recently, this was Hollowwood and company, and then more recently using fractional instantons that with twisted boundary conditions, the topological charge can be fractionally quantized. And using fractional instantons, recently Popitz and Amber derived also this weak coupling result. So this can be put on the lattice. I have some backup slides if you want more details at the end, but let me go to the results we obtained. So we have simulated this and computed the condensate in these units for different values of n. We observe no independence. For instance, here I'm showing this quantity as a function of the pion mass. The points contain the 3 different values of n for different values of the pion mass, and we see no evidence of the strong coupling independence. And also, I plot here this quantity, the gluino condensate, as a function, the continuum extrapolation of the gluino condensate as a function of the lattice spacing, extracted from in two different ways, basically from the density of eigenvalues, the density of eigenvalues of the Dirac operator, and another method similar to the ones we used for computing the quark chiral condensate, extrapolated to the continuum limit. The two methods are in agreement, reasonable agreement with the weak coupling approximation. I mean, here one has to renormalize in some way the gluino condensate. We don't have a non-perturbative renormalization, so we used the perturbative renormalization up to 2 loop order. So there is an uncertainty associated to that. So, I mean, given that, I think, well, this is a quite good agreement with the standard result. And in Susi-Yang-Mills, we have also computed the mass gap, the mass of the gluino glue bound state that can be done on the reduced lattice. We have followed basically the same strategy that for SU2 and SU3 has been followed by these people in this paper. And this is basically the result extrapolated to, I mean, the pion is constructed out of the gluino and the quenched gluino. One can construct what is called an adjoint pion, and supersymmetry is restored in the limit in which this adjoint pion, the mass of this adjoint pion goes to 0. So this is the supersymmetric limit. This is the result that we obtain in SU infinity, and this is the SU3 and the SU2 results that have been obtained in this paper. So there is a rather good, I mean, the infinite n result does not differ much from the finite n values. Okay, so I think with this I conclude. Has taken a bit longer than expected, sorry. So I leave the conclusions there, and we can, if you have any further questions, we can go to that if you want. Thanks.
Thank you, Margarita, for a wonderful talk. I have some questions, but let's see what other questions people have in the audience. So please just jump in with the questions if you have them.
Since I already asked about 2D, like, have you considered doing an adjoint, like 2D theory with an adjoint fermion?
No, but that's also a possibility, yeah.
Would that be possible?
Yeah, it is possible, yeah, it is possible.
Because we've been working here
I know,
a lot using the Hamiltonian approach. And
yeah, I know. So it would be nice to, yeah, this is, it's possible to do, I mean, yeah, we would have to, yeah, we don't have a code for that, but it is possible, yeah.
But presumably it would be easier for you than doing the 4D case.
It is cheaper, yeah, it is cheaper than doing the 4D case, yeah. It could be possible, yeah, to do that. Yeah, I take note of that. Yeah, but I know that you have been working, yeah, in, yeah, QCD2 with adjoint fermions, yeah.
Yeah, just one Majorana. I don't know if it's easy for you or not. But,
well, the n=1 is also one Majorana, so
yeah.
It would be the same, but in 2 dimensions, yeah.
Yeah, we have various other cross checks on that model, and it's actually also supersymmetric for, but not for 0 fermion mass, but for some special fermion mass.
So then in that case, what would be the interesting quantities to determine? So is there any open issue or?
Well, there are like a string tension, computing that would be interesting. I think there are various things, you know, vacuum structure.
Yeah.
We can talk more about it next week in person, but yeah, I think there are open questions. Some things that are hard to study using without just a direct lattice simulation.
Yeah. So it has not been tried in standard simulations?
No, it's been tried using light cone and also the Hamiltonian recently, Silvio Pufu, and you'll probably hear talks about it.
Yeah, I've seen that there are talks about that in the conference.
For example, yeah, actually, so Georg Bergner and collaborators, they computed using standard method and obtained.
Oh, there is a recent paper,
but only for small n. But then
there is a recent paper by Berner and Mithat and yeah.
For small n.
Yeah, that's right.
But for large n, if you could determine gluino condensate, for example, I think would be interesting.
Yeah. Yeah. Okay, thanks. Yeah.
Can you say again what the challenge with glue balls is in this formalism?
Yeah, I mean, in this formalism, you can compute a single trace operator without problems,
Okay.
without any problem, single trace. But if you want to compute a glue ball, then you have to compute the correlator of a plaquette at time 0, for instance, and a plaquette at time t, for instance. Okay, this is a correlator.
Okay.
Now, the reduced lattice doesn't have time dependence because the gauge fields are periodic in time. So the plaquette at time 0 and the plaquette at time t are identical. I mean, glue balls, if you use it's not only factorization. Okay. The glue ball correlator is to extract the mass of the glue ball, you have to go subleading in n, right? Because it's a subleading effect. But moreover, in the reduced lattice, you have to introduce in some way the time separation because a plaquette is independent of the shifts, right? I can compute a Wilson loop, by shifting, but if I compute a plaquette at one point, it's identical to the replicated plaquette in any other point. So I don't have a trivial way to introduce the time dependence in the correlator to extract the glue ball mass.
I think I'm missing something very basic, which is why wouldn't this be a problem for anything that involves correlation functions? After all, consider a meson. You can think of a meson as a single loop thing. And I have a single loop thing here, a single loop thing there.
Yeah, but the thing for instance, if I go back to the determination of the meson spectrum, okay?
Yeah.
You can construct a fermion propagator in momentum space. I mean, in this way. I mean, you have. Can I draw this? No.
Are you using this extended lattice thing to?
You do the extended lattice, okay? And then for the fermion, you get dependence on momentum in this way. But if I do that for a loop that I have here, so you see this link is displaced in this way, But if I construct the gauge invariant operator here, that is a trace, and I displace it, I obtain the same thing. And I displace it, I obtain the same thing. So I'm not introducing any dependence when I displace the trace of plaquette, right?
Right.
So I don't capture any time dependence there. So it cannot be done trivially like that. One option would be to reduce in 3 dimensions and then keep time unreduced.
Right.
We are going to try that, but it's not clear whether that would work. So this is what we are going to try next. But I mean, you have to recover because it's trace plaquette that you're computing, and this is invariant under.
Yeah, I think I see what you're saying. Yeah.
And in a sense, it has to do. This is something that was in the old times of Eguchi-Kawai was also a problem there because. Due to factorization, I mean, double trace operators, to compute the glue ball mass, you have to go subleading in n, and this is not really capturing subleading in n effects. Subleading in n effects are finite volume effects in this context. So,
right. And you want to throw that out, yeah. I think I see the point.
So it's complicated. For instance, other things that it's difficult to do is topological susceptibility, because again, it's a double trace operator, a correlator of that sort that you have to compute. It's complicated also.
I see. Oh, very interesting.
So these are open questions that were open already in the times of Eguchi-Kawai, how to do these things, right?
I see.
So it would be, well, we are going to try several things to try to extract the glue balls, but it's not clear whether they will work or not. But this is our next project, is trying to do that.
But somehow the string tension is not a problem.
The string tension extracted from Wilson loops is not a problem, because the Wilson loops you construct in this way. I mean, you can. This is the loops that I was. I mean, closed loops that extend over the lattice. You just multiply several times. This is precisely the equivalence that Eguchi-Kawai gives for you. I mean, Wilson loops in the 2 lattices are equivalent. Okay. This is precisely what Eguchi-Kawai, the original Eguchi-Kawai proposal is precisely that. Wilson loops in the two lattices are equivalent.
I see.
If the symmetry is unbroken, okay.
Mm-hmm.
But a Wilson loop is a single trace operator. It's not, you compute the expectation value of a single trace.
Yeah, I understand. I see. Yeah, very interesting.
Mm-hmm.
Are there other questions? I have.
If I can ask, you mentioned that it's problematic to compute the topological susceptibility, but is the problem in the susceptibility or in the topological charge itself? Or another way to formulate the question.
No, the topological charge itself, we don't know how to compute for these lattices. Yeah. I mean, in this, you have to think that what the reduction is doing is mapping all the spatial dependence of the objects into the matrix in some way. So the way that people compute, for instance, the topological charge on the lattice, well, there are different ways, but you can use, I don't know, these field theoretical definitions that is basically a way to write FF tilde on the lattice and integrate it over the volume of the lattice. So in the single plaquette model, FF tilde is just the product of two plaquettes. You can do some smearing or something like that, but this is not trivially giving you, we don't see that trivially gives you the charge in these reduced lattices. So we have been trying to analyze also the zero modes of the Dirac operator, either overlap or Wilson. We are working on that, but it's not completely clear yet. So one has to find a way to map the charge into something that can be constructed out of the SUN matrices. And yeah, it's an open issue.
Sorry, but in the field theoretical definition, you don't use a clover, of course, because you don't have a clover, right? Okay.
You can construct a clover if you want.
Okay.
Yeah, with I mean, you can do the clover going backwards, and yeah, you can do the clover also, and then take FF tilde, but it's just, I mean, you don't have volume average, it's group average in this case. So, well, it's not clear that would work in a sense.
Right.
Thank you.
I have one hopefully short question. How does the numerical cost of calculating the string tension using twisted Eguchi-Kawai compare to doing it using a sort of more standard lattice, but with large N in both cases?
You have to do the extrapolation, you say.
Yeah, I understand. Yeah, so like imagine you try to compute the string tension of pure Yang-Mills at large N using the standard lattice with an extrapolation built in, because that's unavoidable with the standard lattice approach, I think. Or with twisted Eguchi-Kawai, which in some sense is automatically at large N, you have no choice but to work at large N from the very beginning. How does the numerical cost compare? Do you have any feeling for that? Is one
so I think that I mean the number of degrees of freedom for the TEK case is basically just the lattice. Okay, so for instance, I told you that this is equivalent to a square root of n to the 4 lattice.
Yeah.
And this is the number of degrees of freedom. Okay, multiplying large matrices is more complicated. So it's not just, the cost is not just only the number of degrees of freedom. But in the other case, you have to do several simulations at various values of n. Yes. And then extrapolate and also take continuum limits for all those values of n. So I think this is more costly because you have to do several of them and then extrapolate. But I cannot give you numbers mainly because I don't have an idea of how expensive it is doing the other thing. I would expect TEK to be similar to one large N simulation, one. Before standard lattice, I don't know, say SU8 or whatever, but
I understand.
But you have to do several and then extrapolate. So I think
I see.
For extracting the extrapolated number, this is better.
Great.
Because you
Ca-
just get the number. I mean, you just get the number in the infinite volume, in the infinite time limit without having to extrapolate at the end.
Can I ask maybe a last question?
Yeah.
How do you, measure the autocorrelation between different, let's say, configurations?
How you determine the autocorrelation?
Yeah, I mean, what
in
in a
general
traditional.
or in our case?
Say again?
In general or in our case?
No, in your case.
In our case, well, I mean, you could use a standard method. The kind of techniques that we do to extract, for instance, the errors is using jackknife binning or bootstrap, or I mean, any of these techniques.
Yeah, I mean, yeah. My question, is related mostly to the fact that since you cannot extract, let's say, the topological charge,
Yeah.
so you cannot claim that you have like a topological freezing.
Yeah, this is true.
So I mean,
Topological freezing could be an issue that we are not
Yeah.
seeing. Yeah,
okay,
could be.
okay.
Could be because we don't know how to map that. Yeah, but it could be an issue. Yeah, could be an issue.
Okay, thanks.
All right. Well, Margarita, maybe we should wrap up. But thank you so much for the wonderful talk. It's very interesting. I'm
Thanks
looking
to you for the invitation. Yeah.
week, and we can all discuss more in person, brainstorm, ways forward on some of this stuff. Fantastic.
Okay. Thank you
All
very
right.
much to all of you. Yeah.
Yeah.
Ciao.
Guys,
Bye-bye.
Bye.
Ciao.
Bye-bye.